I did just finish a class, but I am safe now, so I'll remove my mask. All right, greetings everyone, and welcome to my engineering open house presentation. I will go ahead and start sharing my screen, and we'll jump right into this presentation. All right, first, I want to thank everybody for coming to this talk. I'm very delighted to do this. Always a great opportunity to talk to prospective students and young students starting their engineering journey. My name is Aaron Noble, and the title of this talk is iPhones, Electric Vehicles, and Renewable Energy, the Critical Role of Mining Engineering in Modern Society. And I think it's going to be a fun talk. I like to keep everything as enjoyable and as fun as possible. I always like to start all of my talks by introducing myself. So my name's Aaron Noble. I'm an associate professor here in the Mining and Minerals Engineering Department at Virginia Tech. And here's a picture of me working in the lab. Looks very similar to probably the screen you're seeing right now. I haven't aged very much since this picture was taken, fortunately. But I want to tell you a little bit about my journey over the last decade or so, because I think it has relevancy in this discussion. So if you go back to the late 2010s, early 2010s, I was actually a student. I was a student here at Virginia Tech, and I got all three of my degrees here. So bachelor's, master's, and PhD. So I am a Hokie through and through. Really enjoy Virginia Tech. I think it's one of the greatest places in the world. So I have a lot of value here, and a lot of that came from me being a student here. It's always funny. And as I'm going to show in a minute, I started my first faculty position in right after this in 2014, and I would do these type of talks and always say, oh, it wasn't that long ago. I was a student here, and then I looked back like last year and realized it was like 15 years since I'd been a student here, and so that made me feel very old, but still young at heart, and I was still a student here, and probably did many of the same things that the freshmen are doing these days. I was doing those same things not that long ago. So right after I got my PhD, I actually was able to get a faculty position at another mining engineering program in West Virginia at West Virginia University, and this was a good experience. I ended up spending 4 years there, met a lot of great people, learned a lot, and it really gave me a good perspective to see another department in another university and compare that to my experience at Virginia Tech. But fortunately, in 2017, my department here had an opening, and I applied for it, and I was very fortunate to be selected as the person who got the job. So they hired me back in 2017, and I've been here for 4 years now on this stint, and just serving as a faculty member. My specialty, and we'll talk about this in a second, but it's mainly mineral processing. And I'm very encouraged to see people attending this and wanting to learn about some maybe uncommon majors like mining engineering. And usually, when we think about mining, we think about getting material out of the ground, right? We think about big equipment and maybe explosives or underground mining and things like that. But as we'll discuss in this talk today, mining involves a lot of other things too. And it's kind of the breadth of what mining engineers do is actually pretty wide. It seems pretty constrained, but in reality, we do a lot of different things. And what I'm primarily interested in is if we have valuable material, how do we extract that out of the rock that we've mined? Right. So once we've gotten something out of the ground and mined it, how do we extract valuable material out of that and create a product that can be sold and used in a manufacturing process or other processes? Um, and so that's really where I fit in and what a lot of my research and teaching is interested in. I always hate to be just a talking head on a screen, and I know some people may be watching this recording down the line. And I think the best way is to tell you a little bit about myself because I think that really helps you understand my perspective. So here's some pictures of me when I was a student. Not that long ago, as I like to say, but maybe 10 or 15 years ago. And these are some pictures of me at different mining sites and different operations. I was very fortunate to get the opportunity to work in Wyoming once, in Montana once, and in Alaska once while I was a student. So while I was a student here, I got several summer internships and incredibly valuable experiences. So the picture of me here in the middle, this was me working in Alaska. Alaska during the summer, really beautiful part of the country, really amazing experience. I got to work underground at an underground mine, which I really enjoyed. I really enjoy geology and the way you can see the rock strata and things like that. Really good time, a lot of fun. But here's pictures of me in Montana working. Right after I had graduated, I worked at a summer job in Montana. And this was the day I got to spend with the blasting crew. So we do a lot of blasting and mining to fragment rock, break it up, and make it easier to dig and things like that. And I think most mining engineers have a story like this, but this was the day they gave me the control box, and I got to press the button and set off the explosives. Day I'll never forget. Really, really good time. So, and here's me with another Virginia Tech mining engineer. We're out inspecting the site before we do it, and this is part of the work that we do. As a professor, this is what I do now. So, some of the things that I do as part of my research, actually, my first project I worked on while I was a faculty at West Virginia was off Earth mining, was space mining. And I debated making this conversation about space mining. I think it's a really hot topic, and I actually just gave a seminar about this last week. But for about 4 years, I was really into space mining research. Looked a lot at asteroids, looked a little bit at Mars, and how we can take some of our knowledge and understanding of terrestrial mining and apply that to this endeavor that we're trying to go after as a society now. So I did that. That was kind of my first job at West Virginia. It's really interesting. And if you're a student in engineering, one thing we always say to like freshman engineers is like, and it's just something we say all the time. It's like, oh, your first job, you'll do something that probably doesn't exist today. And when I was a freshman, I was like, well, that's kind of silly. Like, I think most of the jobs that are out there, we've been doing these things, right? Like engineering, like, I think it's based on a good understanding. And sure enough, the first job I did was something that didn't exist when I was a freshman. So I had to eat my words. And so you guys will probably be in the same boat. The first job you do will probably be something maybe that doesn't even exist today, that's never been done before. And that's part of the reason why we love it. That's why this job is so great. I show this drawing here on the top right. This is actually me when I was a graduate student. The project I got to work on as a graduate student in mining engineering was designing new equipment. And we use a lot of specialized equipment in mining and processing. But there's a lot of ways you can tinker with these things. And this was our project is we wanted to tinker with a very specific mixing device. We mix up a lot of rocks and a lot of materials, and we spend a lot of energy doing that. And so what we said was, hey, can we take some basic scientific principles and reduce that energy requirement? Make this thing more sustainable and cheaper. And we did that, and we actually we got a patent. So here's a U.S. patent, and my name's on that list. So I was one of the inventors on this, and this is something I did when I was, I don't know, 23 years old. Had my first patent, and it was really good, and it was pretty cool. And getting that, we were able to license this patent to a company. So they bought it from us, and they paid us a licensing fee for that. And so that fee gets split between the university and then all the inventors. And so, sure enough, I got a check, and it was not like a tremendous amount of money, but it was a couple $1,000s. And for a graduate student surviving on a stipend, it was like gold. It was really I was really happy to do that. But the reason I tell that story is because I was dating the lady who had become my wife at the time, and I was able to use that patent money to buy a very nice engagement ring. And so I show this picture of this patent to my wife all the time, and she loves it, right? Because that's what we used to buy her engagement ring. But the story doesn't end there. The cool part of this is they actually use this technology now, and they use this technology in some of the biggest mixing devices in the world. So you can see this picture here. It's a little bit small, but that's a person, a pretty large person, standing right there next to this tank. And this is just a big tank. And inside that tank is this mixing device that we designed. And they're selling these, and it's a complete change in the industry. And it's a really fascinating and really cool to be part of that. So I worked on that a little bit, and now, and the focus of this talk we're going to talk about is in critical material processing. And so we're going to talk about what are critical materials, why do we need them, and then what is our research group doing to try to produce them to help society. So and we do a lot of different things as part of this, and we'll talk about this a little bit. But we do very sophisticated microscopic studies. We design and build equipment. But the cool thing is this last picture, when we can actually make a product of a very high purity, valuable material, and it's kind of the culmination of all this work. And when you can hold that in your hands, it's very meaningful, and it's very impactful, and it makes you feel good about the job you do. So the way I structured this talk was, and then kind of getting the introductory information out of the way, I wanted to structure this talk about around some guiding questions. And so as you watch this, we're gonna open up, and we're gonna open up three kind of guiding questions, and we're gonna think about these as we go through. And so, kind of a hard reset now. We're gonna move and look at these. So the first one is kind of the title of the talk, right? It was the title, but I think it's our number one guiding question. What is the role of mining in modern society? And I talk to a lot of people, and they're like, "Mining, isn't that antiquated and old? Are we still doing that?" And I want to address this first because I want to say, what's the role of mining in modern society, and where is mining going, and what is mining about? And so that's what we'll answer first. And I want to answer this question generally, right? So not just about what my group and Virginia Tech's doing, but mining in general. The next thing I want to look at is, what is my team? Aaron Noble's research team here at Virginia Tech. What are we doing to address that and this challenge of critical materials? And we'll talk about critical materials in this first bullet a little bit, but we're also going to talk about how we're addressing this and what specific things we're doing. And hopefully through this, you'll kind of see, and my hope is that you'll be able to see a little bit of yourself in this, because I think we employ a lot of students, and we'll talk about this guy in the picture here, Chris here, and my hope is that you'll see yourself in that, and you'll see, hey, I can do these things, right? And it'll feel very encouraging and very empowering. And then the last thing, we'll give you some action, some call to action. How can you make an impact? So let's talk first about what's the role of mining in modern society. And a couple of years ago, in 2015, I showed this graphic. Some people a lot smarter than me at the United Nations sat around, and they said, as a society, what can we be doing to make things sustainable, right? If we're going to develop society and we're going to grow our economies, what should we be doing to ensure that that is done sustainably? And I'm sure you guys know a lot about sustainable development. It has many different aspects of it. But the way the people at the UN articulated it was they developed these different goals. And these are all very meritorious goals that we should be trying to pursue, I think, as a country, but also as a general society. Things like zero hunger, right? That should be a goal for us. There should be zero hunger in the world. There should be no poverty. There should be decent work and economic growth. There should be gender equality, and all these things. They came up with 17 different things and said if society were doing all these things, it would be very good. And this is what they kind of articulated and came up with. What you see on this graph, the ones that are kind of bigger than the other ones, these are the ones where mining has a very big impact, an ability to make an impact, both negatively to an extent, but also positively. And that's what I'm focused on is mining can create a lot of positive impact. Things like strong institutions, right? So in some countries, mining can help support strong institutions. But one in particular is, I think, this goal number 12: responsible consumption and production. So as a society, if we want to pursue all of these goals, right, we're going to need materials and resources to do it. We're going to need raw materials, we're going to need energy, and we're going to need other things to go after these and build these things up. And if you think about all these, if they all have some input to them. They don't just happen spontaneously, but they have some input. And oftentimes that input starts with mining. And that's why I think this goal 12 is so important, because it's not just about mining, but how can we do it responsibly, right? How can we do it while honoring these other things and not making things worse? And that's the way modern mining is, and that's the way we teach it here. Is we understand mining is essential, but it also has to be done responsibly, because you can make a big impact, right? And that's what we want to do. We want to create a big positive impact. And so I show this picture here. My neighbor has one of these. He has a very nice Tesla. I unfortunately do not. This is not my car. But if you look at things like this, and I talk about growing the economy, but going the direction we want to go as a society, perhaps that involves more electric vehicles, right? Less dependence on fossil fuels and a lower carbon footprint. If we look at the technologies needed to do that, and this is what is written over here in text, maybe better articulated when I had time to think about it. But if we want to do that as a society, if we look at the raw materials needed to get there, they're becoming increasingly sophisticated and increasingly complex. And so something like this Tesla has many, many elements in it. We're going to look at a very specific and a very revealing example in a second. And all those elements, all those different things have to be mined. And some of them are very large commodities like aluminum. We can get a lot of aluminum very easily, but some of them are very sophisticated metals, very hard to acquire metals. And that's where the idea of criticality comes in. So things that are very essential to where we want to go as a society, but may have a very poor supply chain, we call those critical. And they're critical because they're hard to get, and we have to come up with better techniques and better processing and better mining to go after them. And that's kind of what the takeaway here is if we look at this and say, hey, we want to make more Teslas, it's going to require materials to get there. And I show this, and this is a really good example. I put this slide together last night. Take a common device like your iPhone, right? And I don't use an iPhone. I use a Samsung. Should have shown a picture of one, but I know a lot of people like iPhones, so I showed that here. So say you have an iPhone, and think about the materials that go into creating this iPhone. And many people are maybe in chemistry, and I'm doing my best not to make this a chemistry lesson. But if you think about the chemistry, I mean, think about the periodic table. There's 120 give or take elements on it. How many of those elements do you think show up in the iPhone? And I looked at it, and I made this plot last night. It's about 75 elements, right? So the majority of the periodic table shows up in this iPhone, and some at pretty notable concentrations. Some are just very minor. But to make this fairly simple device that we all carry around every day, you need 75 different elements. And each one of these would have to be mined and come from a different location and have a different supply chain. So you can think about all the effort that has to go into making something like this that we make millions and millions of a year. The corollary to this, what I want to show is take something else that's very very complex, like you and me, right? We're pretty complicated, complex beings. Humans actually only have 27 elements on the periodic table. So, and I realize that a lot of this is organic, so maybe it's more complex structure or whatever. But just from a raw number of materials present, iPhones are much more complex than we are. And that's kind of crazy if you think about it and you look at that comparison. And we start thinking not just about iPhones, but all these other things we want to do as a society. The need and the demand for metals is just growing incredibly, and so society's demand for materials is just on a skyrocket, right? And as we get into more of this, I think we're going to see a greater demand for that. One question that always comes up, and I was talking to my wife about this morning, is the question of recycling. And I think there's definitely a place for recycling. And if we want to have responsible consumption and production, recycling is essential. So we don't need to be tossing these things, but we need to be trying to recover these metals and putting them back into the supply chain. And the example I gave was aluminum, right? If we look at aluminum, a tremendous amount of aluminum is recycled. Like 97% of aluminum is recycled, and we still mine a lot of aluminum, right? Because that's what society's demand, society's appetite is. And the other cool thing is, I actually do a lot of recycling projects, and the technologies. If you look at it on a fundamental level, the things that are used in recycling are also used in mining. A lot of the same processing technologies. And so I have many graduate students and undergraduate students that out of graduation, they go work for recycling companies because the training they got as mining engineers sets them up very, very well for that industry because a lot of it technically is very similar. One we're going to look at specifically are a group of elements called the rare earth elements. This is where a lot of my research is in. And when we say rare earth elements, I draw the periodic table up here, but it's intentionally small, so you don't have to worry about it. It's these group of materials down in the nether regions of the periodic table, as I like to say, ones you probably don't even learn in high school or anything. But these are a group of materials that are very important because you just find them everywhere. And I look here at a Prius. This is a little bit of a dated picture, but things like the glass, has certain rare earth elements in it. But the big one is anytime you get to a motor, a small motor that are in a lot of electronical components, they have very small magnets in them. And those magnets come from neodymium, which is down here, a very, very important rare earth element. And you can start, your imagination can go wild everywhere you see small motors, but they require these rare earth elements. Rare earths are extremely critical because they have a very, very niche supply chain. And we're going to talk about this in a second and what can happen to it. Um, and here's some other things. I just put this on here. So rare earth elements, you find them in all these modern technologies, airplanes, windmills. We'll talk about windmills in a second. Obviously, the Prius, iPhone. Don't want to neglect defense applications. So things like satellites and things that DoD uses that they don't tell us about. They contain a lot of rare earth elements, computer hard drives, and even baseball bats. Baseball bats use a lot of scandium, very specific element, creates a very nice aluminum alloy. So it's like all this modern stuff and baseball bats all require rare earth elements. But where do we get these from? Where are they being mined today? And what are the practices being used for that mining? And the unfortunate truth is in the US, we do very, very little. We have one rare earth mine, and that rare earth mine actually exports everything. So there's no domestic supply chain for rare earths. Rather, we import all these components, with the vast majority coming from China. And so in this graph's a little bit dated. This is 2008, so it's actually been a while ago, but things haven't changed much since then. About 95% of the rare earths come from China. And in China, they only come from a handful of companies and a handful of mines. And so if you look at these materials, rare earth elements, absolutely essential ingredients for modern technology and a very, very restricted supply chain coming from just a handful of players. And you don't have to think very long to think how this can create a very sticky situation. And is this a big deal? So I went last night onto my computer and typed in rare earth elements and pulled up some news articles from the Google. And you see a lot of things that are just like doomsday, like Chicken Little stuff. So, China has the US by the throat. China tightens rules. China worries over supply disruption. And you can get thousands of articles like this. These are just in the last like 2 days, right? And you get all these articles about doomsday for what's the US going to do without a sustainable supply of rare earths. But what's the implication? What happens when this occurs? And you can tell I'm an engineer because I show a lot of plots and a lot of data in my presentation, and then I like to explain this. So what this is here, this is not GameStop stock price, right? It almost looks like it. When I looked at this the other day, I was like, hey, this looks like GameStop. This is not GameStop, I should say, stock prices. This is actually rare earth prices from 2010 to 2014. So it's a little bit dated, but it indicates what can happen. And so remember, you have a very important material that is supplied by just a handful of players. And this is the prices indexed to whatever they were on January 10th. So if you go from January 10th to June, or January 2010 to June 2011, so about 18 months later, some of these things were going up by as much as 4,000%. So like 40 times more expensive than they were a year ago. And there's some geopolitical reasons for this. If I remember correctly, there was like a fishing boat incident, and China got into a trade disagreement with Japan, but they essentially cut off the supply, and they said, we're gonna not supply any more rare earths. It created an instant shortage, an overnight shortage, and all these prices shot up instantly. And you could imagine like anything you want to go buy, imagine it going up 40 times overnight. Like I'm going to go buy Chick-fil-A for dinner, and then I go tomorrow and it's 40 times more expensive. I'm probably not going to Chick-fil-A for dinner, right? And that's true of everything. It was also true for rare earths. So what are rare earths used a lot in? They're used a lot in magnets and in these motors and things like that. And it's interesting, one of the big uses for them are in these drivetrains for windmills. And I'm not a windmill expert, but I do a little bit of reading. There's apparently two different ways you can build these. One is with a technology called DFIG, which is the drivetrain that uses kind of very easy to get materials, and then there's the permanent magnet drivetrain that uses neodymium. And if you think back to what this country was doing in this time, they were installing a lot of windmill capacity. There's a tremendous amount of windmills installed in this time frame in the U.S. And from what I'm told, most of them use the DFIG technology, which is inferior, right? We would rather use the rare earth magnets for windmills because they're a lot more efficient. They operate over a larger range of speeds and things like that. But if we can't get those rare earths, we substitute it for something inferior. So if prices go up and I can't go to Chick-fil-A, then I've got to settle for something else. I've got to go to Burger King for dinner, and I'm going to get an inferior product. That's not a indictment against Burger King, but I think you guys get the analogy. And so the same thing, when the prices went up, they couldn't build those nice windmills that they really wanted because they were too expensive. So much of the windmill capacity installed in the U.S. is actually suboptimal, right, based on a material shortage. And this is what can happen, right? And I always try to think about what would be different in the world had we had those materials. We could have put in the higher capacity ones, and maybe the world would be a lot different now. But it all comes back to mining, right? It all comes back to these critical materials, and how do we get our hands on them? And so I read a lot about this, and I was very motivated, and I said, hey, I'm like you guys. I love my job, but I also want to make an impact on society, right? I want to make an impact on individuals. I want to make my students better and my team better, but I also want to do something that can potentially change things. So I said, how is my team addressing these? And so if I go back a couple slides to these news articles, you'll see one here interesting. I skipped over it, but it says, "Can harvesting rare earth elements solve the coal ash crisis?" What do you mean by that? Is there something to do with rare earths and coal ash? And if we go back a little bit, I like a little bit of history, and we go back to 1952. There was this professor at Penn State, and this is actually what the name of it was then, the Penn State College. And this professor said, by the year 2000, we will not be wasting coal ash. Where we found there's a notable concentration of these rare elements, rare earths and uranium and other things. We'll be recovering these. Now, Dr. Estito was very, very smart, but he did miss the year, right? We're a little bit past 2000. But the thought was correct that, hey, there's wastes, maybe like even coal wastes and other industrial wastes that contain these valuable materials that we're after. And so what I said was, what's the missing link? Why aren't we exploiting that? And while we've known about them for a long time, we've known about this resource, right? We've known about this resource potentially in these waste products since at least 1950, right? That Dr. Steele knew that. Very recently, there's this huge market demand growing, right? With all these advanced materials and advanced things that we need. What's missing are the processes. How do we actually recover these things? And can we do it economically and in an environmentally benign manner? That's where the technology is missing. And that's where the research comes in and where my group came in. We found this missing link and we said, how can we address this? And so our approach in 2016, we've been working on these projects for about 5 years now. We started looking at mining wastes as a potential source of critical materials. And there's some things that I think we want to ensure a responsible, like I said on the first slide, responsible consumption and production. And mining does produce a little bit of waste, usually just ground up rock and ore and things like that. And usually you kind of leave them in around the mining site, or you can put them back underground and things like that. Here's some pictures of just some ponds and things like that. But we started looking at these and we said, hey, let's look a little bit closer. We use very sophisticated technology and we started identifying if the critical materials were there, at what concentrations and in what form. And it was shocking seeing the results because there's a lot there. But like I said, the process technology is just missing. And so I like this approach, and one reason I really like this approach is because we can go back to some of these legacy issues, maybe from the 1960s and 1950s, where mining may not have been done as responsibly as it should be today, or as it is today. And we said, hey, can we go back to those old wastes, these legacy issues, and incentivize people to clean them up, right? And so that's what I said. So not only are we meeting the societal need of critical materials, but we're also incentivizing environmental stewardship. So we're gonna people can go back and see these um, environmental liabilities and turn them into revenue streams and turn it into a really good win-win situation. But the key is the process. And so like I said, we've been working on these for a while, and some of them are still going. But the general approach we follow, I call this process development research. We first get a sample and we get the material that we're looking at. And like I said, we use very sophisticated technology. This picture here, it's a little bit small, but this is like a couple micron size particle. So think about the size of the tip of your hair, right? It's a very, very tiny particle. And we actually mined this particle, this tiny, tiny particle, by using a laser beam. And so we use a laser beam and we actually cut out the particle and we can extract it. And then we can analyze that one particle and know exactly what it is. And that informs us on what's in the entire lot of that giant pond you saw, because we can see it and we can analyze it specifically. So very cool process, very expensive process, but very cool. We did that. We then start scaling this up. So we take lab tests and we do our lab tests to see how we concentrated and what kind of processes we can develop. And this is where a lot of the fun happens. This is where the magic happens, and where a lot of the student researchers get involved, where they come in with ideas, and we can play around with physical properties and chemical properties, and see how things are going to respond. And we use some fun equipment, and we break things, and it's a really, really good time. This is really the good time, the laboratory testing. And then where I come in is usually in the middle here. So we have groups that focus on this, and then they give me all their data, and I tell them how much it's going to cost commercially if we want to deploy this commercially. So we do simulations. We take the data and we model it, and we build mathematical representations, and then we can do cost analyses. We can figure out how much revenue we're going to be generating per year. We can look at different scenarios and different commercialization scenarios, and we double check and see if it makes sense. And if it does, then we can go forward with doing maybe engineering design, where we come up with models of what this plant would look like, right? And so here's an example of one of the plants. And then eventually in the research process, we may get to build a plant, build a small pilot plant, which we've done this a couple times now. Here's a picture of one that we built in Kentucky. And you can go there and you can put coal waste in on one side and get rare earths out on the other. And all the magic happens in the middle. And it's pretty cool to see that. And it's pretty cool to see it at scale. And the fun thing is we get our students involved with this, from step one. So I'd say over the last 5 years, I tried to add it up. I've probably employed 30 to 40 undergraduate researchers in this. We do a ton of research. Many of them have made very, very important contributions. And I thought about this presentation. I thought, hey, we could go into some of the detail, on some of these, like, parts of the research and the pilot plant and all that. But I thought it'd be better to talk about a story of an individual, right? And you may be able to see yourself as this individual, because I think many of you will, right? I think many of you are going to do really phenomenal things, and this is a good indication of that. So this gentleman here, a really good friend of mine, but a student who had worked in my group for 3 years, Chris Osterhout, and then he just graduated last year, and he's now working in Ohio for a mining company there. But in his research, as part of an undergraduate, he developed a process that essentially reduces our separation cost by more than 50%. which that is just a phenomenal number. It's an incredible number when we talk about cost reduction. And so he did all the, we looked at some papers. We did a lot of reading on what people had done before. We took those ideas and modified them. He developed an experimental program and an experimental methodology. He went to the lab, made all of his samples, ran the test, analyzed the data, found the optimal points, followed a very, kind of standard experimental research approach. And it turns out that it was very good. It was a very impressive result. And then the good takeaway, he made a poster on these, and he gave a poster presentation at this national research contest, and he came in first place. He got first place honors in that, and was given a $1,000 check right there. And then he refused to take us all to dinner afterwards, even though he got the $1,000 check. And this isn't uncommon. I asked my other students for pictures. So I sent an email like a couple days ago and asked 3 or 4 of my students for pictures, and no one sent any. So I was like, okay, you're not getting in the presentation since you didn't send a picture. But Chris did, and he gets highlighted here. But we've had a couple of people win first place honors in this. And then here's a picture of his poster, and this is what he did as an undergraduate. So like I said, he kind of talked about the literature he read. You can see the obligatory periodic table there with the rare earth elements highlighted. And there's the test he actually ran. So he's creating a column of foam, and then he's using foam to separate out different elements, which is pretty cool. And then here's his data analysis. We use some software, and then you can see where the high points and low points are. And from this, you can make projections on how this would behave. So really cool and really great job, and really proud of what Chris has done. So how can you make an impact? If you look at mining in general, so we talk about critical materials, and then I think that's an important subset, but we also mine a lot of other essential items like, iron ore and copper. Copper is absolutely essential to an electrified economy. If you think about how much copper goes into the electric vehicles and things like that, we could give a whole presentation on that. And the truth of it is, a lot of those materials do have to be mined, and that mining needs to be done in a manner that's responsible and environmentally acceptable and socially acceptable, and something that generates a lot of benefit for the communities. And that's the way we teach it, and that's the way we do it here at Virginia Tech. And I think this is important because if you look at mining, the big picture, here's a big open pit mine. Mining are probably some of the most large, expensive, and impactful human endeavors. And because of that, they have to be engineered, and have to be engineered very well. And I was thinking of like the very first mining class I took. I can't take credit for this, but the professor walked in and it was like, anyone can go dig a hole in their backyard, right? And we could probably dig a pretty deep hole if we wanted to, if we set our minds to it. If we wanted to dig a mile deep hole and do so in a manner that can produce money and produce jobs and minimize or mitigate any environmental harm, that's a much different story than digging a hole in your backyard. And that's why mining needs very, very skilled engineers. And so we think about human activity, and we think about the human activity that requires engineers to support that development. Mining is number one on the list because it's so impactful to society, and it has such a positive impact. It can have such a positive impact if it's done well, and it can have such a negative impact if it's not done well. And because that risk is there, I think we need very, very good engineers. And so the motto of our department, and this is our mission statement here on the left, and I'll just read this. Usually don't read from slides, but it says, "We serve society through education and innovation to support safe, efficient, and environmentally responsible production of energy and mineral resources." And this really gets at who we are as a department. I like the first line, "We serve society." And as you learn more about Virginia Tech, you'll know that our motto as a university is "Ut prosum, that I may serve." And so we start our this by saying we serve society. That's our lot in life. And the things we do are education and innovation. So we teach and train students, and then we do groundbreaking research like what you saw. And then what we're after is safe, efficient, and environmentally responsible production. And so I think this is a really good statement because it says that's what we want to do. And as I always say, I think the world would be so much better with more hokey mining engineers out there. And there are a lot of us. If you look back since 2000, like 25% of the mining engineers in this country have come from Virginia Tech, which is just a crazy number. 25% of mining engineers from Virginia Tech. But if that number is like, I want even more, right? I want to have even more Virginia Tech mining engineers out there because I think that's what gets us to a much better outcome. I always get this question a lot. If I'm a mining engineer, am I just going to be working underground like these folks here every day? I loved working underground. I found it very fun, very enjoyable, but it's not for everybody. And the truth is, with a mining engineering degree, it actually gives you pretty broad career opportunities. You may not think that, but it's not like you're just restricted to working underground in a mine. I give some things here. One good example, like finance, right? And I know a lot of people are always interested in finance. I love finance and investing and things like that. One of my really good friends, he's a mining engineer, and he spent a good portion of his career working for a bank and doing finance, right? And his job was to go to mines and see if they were worth investing in and do due diligence on mines. And so that technical background allowed him to go in and say, okay, is your operation doing this in a way that's efficient and responsible and all that? And he could look at it through that technical lens, but then he could go back to the bank and say, okay, based on this and based on our capital allocations, how do we pay for it? And so that's pretty cool, right? So he's a mining engineer, but he doesn't work at the mines. He works for a bank, which is very interesting. I do research. So I would fit under this group. Sales. I had a really good friend of mine who's now a graduate student. He worked in sales for a long time, and he sold chemicals. And he sold chemicals to the mining sector, but to other sectors too. Got to do a lot of travel. Got to go to a lot of different operations around the U.S., a little bit internationally. But his job was to go and speak to the engineers on site and convince them to buy certain chemical packages. And so that's another way you can use your degree and the technical knowledge you have, but you're not just working at a mine, right? And however, if you do want to work at mines, we have a lot of students that do. They go into operations and they want to be there on the front lines and really, they have a team of workers and they're leading their crew of 10 to 20 people, and that's a really cool part too because you really get to see things hands on. So I think there's a tremendous amount of career outlooks for mining engineers, not just restricted to working at a mine and doing one thing and being very bored, but tremendous amount of opportunity around a full spectrum of potential careers. I show this up here. I was thinking about removing this slide, but this is just some highlights from our department. So things like our class sizes are usually pretty small, 30 to 40 students. I like to learn all my students' names on the first day. We do a tremendous amount of research. So I think our department has traditionally had some of the highest research activity in the college per faculty member, and we do employ a lot of undergraduates. I think I've got 6 or 7 on my team right now, and then a number of graduate students. We also do very well with job placements and interns. Like I said, Virginia Tech supplying about 25% of the since 2000, 25% of the mining engineering graduates, and there's always a lot more jobs than there are students to fill those jobs. So most of our students come out with multiple offers, and then they can choose between 2, 3, 4 offers, which is incredible. And some of the times when the markets are crazy, mining is usually still pretty strong. And then just about everybody does an internship. And as you saw, I loved my internships and really highly recommend it. Won't go through all of these, but if you take a screenshot, you can always come back and look at this later. But with that, if you have any questions, my name's Aaron Noble. I've really enjoyed giving this talk, and I'll be happy to answer any questions you have right now. If not, I list my email address here, so you can contact me directly. You can also check out our website, our Facebook. I think we have Facebook, Twitter, maybe Instagram. Check out our posts on social media. We do a lot of things with what our students are doing, what our graduate students are doing. If one of our professors wins an award or something, we'll post that as well. And then sometimes we get our alumni. I really like the alumni stories. We get alumni to say, "Hey, here's what I'm doing at my job," and we post that on Facebook. So we try to keep that pretty active. And so please follow us, like us, and with that, I will shut this down and answer any questions you may have. All right, so we have one question come in that says, "When do engineering students usually intern?" And so it's a really good question. Thank you for asking that, and I appreciate that. Our internships are usually during the summer. And so my department is unique in that we do our own kind of career services, almost like our own recruiting with companies. And so companies, we have our own. First, we have like a mining career fair where we'll have 20 or 30 mining companies come, and then each week we have other companies come in, and then they'll interview for both interns and full time employment. The internships are usually during the summer, so students will do an internship during the summer months, and that's usually negotiated with the company. When I did mine, I would start like the week after school was over, so like May 14th, and I would work until one week before school starts because after I did one, I really enjoyed it, so I would always try to maximize the time at those internships. Another option which I didn't discuss is co-ops. So as you learn more about it, usually internships imply just a summer. Maybe you can do it over winter, although winter is there's only like 4 weeks of winter break at Virginia Tech, so it's not that much. So internships are usually meaning like a summer work. Co-ops are over a full year. And so the way a co-op would work is you would say you would complete your spring semester, and then rather than going to school in the fall semester, you would go to a company, and then you would work for one full calendar year, and then you would resume the next fall. And so usually it can set you back a year in school. I did not do a co-op, but I know a lot of people that do, and we have some companies that have very very strong co-op co-op programs, not problems, very strong co-op um, programs. And the benefit of a co-op is you get such good detailed experience. Because the summer is usually 12 weeks, even if you extend it, there's only so much you can learn over 12 weeks. But over a full year, you essentially become like a staff engineer at these sites, and they'll give you very large responsibilities, more than you think you should be doing, right? But the companies do find benefit in that, and that, right? And they usually have really good mentorship programs, so you'll be aligned with like a senior engineer, and you'll be doing you'll be doing actual engineering work for a good year. And it also allows you to evaluate different parts of the business. So over the year they may put you in one business segment, but then they may move you around too. It really depends on the program. But just for the nomenclature, internship usually implies summer, and then co-op would imply a full year or some break with the semester. But really great question. The other thing is, I know in my department, and I would say with most engineering disciplines, the internships are paid, and they're paid at a fairly good competitive wage. I talked to some of my friends in other areas, not in engineering, but the expectation are unpaid internships, and I just shake my head at that, because for engineering, and specifically in particular mining engineering, the companies that you have to pay competitive. It's not that you can't pay anything; it's like you have to pay something, and it has to be competitive, or students will go work at other internships. And so I know, like when I was a student, um, like I said, in the like in the late 2000s, it wasn't uncommon that you could make $15,000 over a summer, like $10,000 to $15,000, working your internship. Like that was kind of what you'd make. And I'd say students now, you could probably make that same, or maybe 15 or even more, because I'm sure wages have gone up. But based on what you got paid, you could easily make 10, 12, maybe $15,000 over a summer. Which when you're a college student, that was just incredible that you could do that. The other thing in my department is we have a very good scholarship program. And we handle this within the mining department. The mining industry is extremely good at giving back, and I think it's very unique. But we have a very strong alumni base and a very strong industrial base that want to really support students, and not just say they support students, but back it up with their contributions. And so we get a tremendous amount of scholarships that we can give out to our students. I used to know the numbers specifically. I apologize, I don't know them now. They may be on the website. But it's a pretty simple application. You fill it out, and if you have a reasonable GPA, then the department will fund you a scholarship. So between scholarships and internships, I think it sets you up for a pretty good financial situation, specifically in mining engineering. But also most departments in the college do things very similarly, and would have very good scholarship programs. For anyone watching this video in the future, I do want to just thank you for sticking around to the very end. Really been a pleasure to talk to everybody today. Really enjoyed it, and I do wish you the best in everything going forward. If you ever end up in one of my classes, please let me know and say, "Hey, we saw you on Zoom on that recording several years ago," and then it'd be great. We can reminisce about that and talk about how the presentation went. But with that, thank you everybody, and take care.